This week we are beginning the topic of equilibrium. You can find this handout posted under Canvas and in the announcement. I would recommend printing it or pulling it up on your iPad and filling it out as we go along. In order to talk about the concept of equilibrium, we first have to start with the idea that reactions can be reversible. This is new to us. We haven't really talked about this idea before. Up until now, we have thought of reactions as pretty much always going from reactant to product. It moves one way. We start with reactants and we make products. But the reality is that there are a lot of reactions that can be reversible. So reactions can go forward from reactant to product, and they can also go backwards, having product form reactant. Not all reactions are reversible. For example, you cannot unbake a cake or uncook an egg. Some reactions, once they happen, they can't go backwards. But other reactions can. Some of the sort of simple examples of reactions that are reversible include phase changes, right? We can freeze and unfreeze water as much as we want. All we have to do is change the temperature. So we can get it to melt, we can get it to freeze. It can go both ways. So when we have a reaction that's reversible, we use this double-sided arrow to indicate that it's a reversible reaction. It can go both ways. Another example of a reversible reaction is dissolving salt in water, right? We can take solid salt and add it to water, and we can end up with aqueous ions. If we want to, we can get the reaction to go backwards by evaporating the water. So we can dissolve and evaporate, and we can get this reaction to go in both directions. When reactions are reversible, it is possible for both the product and the reactant to exist in a constant ratio because the reaction can go in both directions. When this happens, we establish something called dynamic equilibrium. Whenever we talk about equilibrium in this class, I'm going to say equilibrium, but I really mean dynamic equilibrium. So let's explore what this means. We're going to use the concept of dissolving salt to think about this. So if we had a beaker of salt water, or a beaker of, let's just say, water. There's our beaker of water, and we added salt to it. And I'm not going to be able to draw this really well, but let's say we started sprinkling salt into our beaker of water. There's our salt falling in, right? When you first start adding that salt, it's going to dissolve and the solution's going to be clear and you're not going to know. But if you add enough, eventually you're going to come to a situation where it won't all dissolve. And we're going to have some salt crystals sitting on the bottom of the beaker. This is known as having a saturated solution, right? We have as much dissolved as it will. When we reach the saturation point, we have established a dynamic equilibrium. What's happening here is that the reaction is still happening. We have solid sodium chloride dissolving and going into the water. At the same time, we have sodium chloride coming out of the water, right? So this is happening back and forth, in and out. The reaction is happening constantly at a constant rate. So if we were to just look at that beaker, it would look like it's not changing, but the reaction is actually constantly happening. So it's kind of like a duck on water. It looks like it's kind of smooth and sitting there, but underneath the legs are going crazy. Dynamic equilibrium is this way. It's a reaction. It's taking place constantly, but it's going both forwards and backwards. So it looks like it's not changing. Let's put this to notes. So we have a reaction taking place in both directions at a constant rate. A reaction taking place in both directions at a constant rate. And so even though the reaction is taking place, it appears like the reaction has stopped because the concentrations stop changing. Concentrations are not changing, so it appears like the reaction has stopped. And so these make up the two components of dynamic equilibrium. The reaction is taking place, that's the dynamic part. The equilibrium part is that the concentrations are not changing, so it looks like the reaction has stopped. All reactions at equilibrium are defined by something called an equilibrium constant, or Kc. Kc is a constant that is unique to each reaction. To look at what Kc tells us, we're going to have to kind of use a standard reaction. So we're going to use the reaction AAs plus BBs make CCs and DDs. That's just going to be our generic form of a chemical reaction that we're going to use. Okay, so Kc is actually a ratio of the products at equilibrium to the reactants at equilibrium. This bracket symbol here is an abbreviation for molarity, or moles per liter. So what this equation is really telling us is it's a ratio of the concentration of the products to the concentration of the reactants. So this is the generic form of the equation, products over reactants. What we do if we're actually working with an equation. So we're going to use our generic equation here to set something up. So the Kc will be equal to the concentration of our products, which are C and D. So the concentration of C raised to the coefficient, the lowercase c, times the concentration of D raised to the coefficient. And then our reactants will be on the bottom, A, the concentration of A raised to the coefficient, and the concentration of B raised to the coefficient. When we write these, it's important to note that we only include substances whose concentration can change. So when we write what's called an equilibrium expression, we do not include pure solids or pure liquids. So pure solids and pure liquids, their concentrations don't change because the ratio between their quantity and their volume is fixed. The concentration of gases can change, the concentrations of solutions can change, but the concentrations of pure liquids and pure solids don't change, so we omit those. One of the things you need to learn how to do in this section is to write an equilibrium expression. So let's practice doing that. I have these two equations here, these two chemical reactions. I want you to take what I did above and apply it and try to write the equilibrium expression for these two practice problems. Pause the video here and resume it when you think you have it. Okay, so the answer for the first one is Na plus concentration times Cl minus concentration over 1, or we could omit that and just write Kc is equal to the concentration of sodium ion times the concentration of chloride ion. We omitted the reactants NaCl solid and H2O liquid because they were a pure solid and a pure liquid, so they don't go in the equilibrium expression. Did you get it right? All right, let's try the next one. The answer for this one is CO squared over CO2. We omit the carbon because it's a pure solid, and don't forget that this one has this 2 here, so we need to include it there. For additional practice, see the worksheet I have posted, and number 1 on the worksheet will give you some more practice with this. Okay, so now that we know what an equilibrium constant Kc is and how to write an equilibrium expression, we're going to talk about what the size of a Kc value tells us, what the magnitude means. And essentially what it's telling us is whether or not a reaction prefers the reactants or the products, or if it sort of favors them equally. To explore this, we're going to think about sort of our generic reaction, AA plus BB goes to CC and DD. So again, we're going to be thinking about this reaction here. And we're going to imagine a scenario where we have a beaker and we put A and B in this beaker. Okay, as the reaction starts to happen, we're going to make some C and D. So we're going to have a combination of A and B and C and D. And then as the reaction continues to happen, we could imagine a scenario where we're left with C and D. So we sort of have these ranges here where we have primarily all reactant or all product or a mixture. So over here in one extreme scenario, we have all reactant. And over here in the other extreme scenario, we have all product. And then we have our sort of middle ground. So we can imagine for a reversible reaction that this could go this way or it could go this way. What Kc is going to tell us essentially is where does a particular reaction find its equilibrium in this range, right? Is it here? Is it mostly reactants? Is it here? Is it mostly product? Or is it somewhere kind of close to the middle and it's a mixture of all things? That's what Kc and the value of Kc is telling us about a reaction. So before we actually go through what would constitute a large, medium, or small Kc, let's remind ourselves what Kc is. Kc essentially here, if we think about the very simplest definition or form of that equation, Kc is the ratio between the products and the reactants. So we want to look at this equation and think about it. If we have a big value for P and a little value for R, what kind of value is going to give us for Kc, right? A big P and a little R, that's going to end up giving us a big number for Kc. And so that's what we get here for a large Kc. We have a lot of product and a little reactant. That's telling us that our reaction has gone almost to completion. We are here. So this is what a large Kc value would tell us. A large Kc value is, now these aren't perfect ranges, these are general ranges, but we'd say a large Kc is something in the order of 10 to the second or greater, if we're using scientific notation. So we're looking at something in the hundreds or higher, thousands and up. And these can get really big. They can be, 10 to the 20th or something like that. So they can be big. An example of a reaction with a large Kc value is the reaction between silver ion in solution and ammonia in solution. So this reaction forms something called a complex ion. It's AgNH3, 2, and that whole thing has a 2+ charge. This particular reaction has a Kc value of 1.5 times 10 to the 7th. For practice here, I'm going to tell you to write an equilibrium expression for this reaction. So when I post the answer key to this online, it'll be there. So practice it and check online and see if you did it right. A medium Kc value would be something that sort of equally favors product and reactant. So if we think back up top here to our equation, if we have sort of equal amounts of product and reactant, then we're going to get a value of Kc that's relatively close to 1. So this is sort of 1. This is going to be our medium Kc value. We get a mixture of both. The range that we're going to kind of go with here is somewhere between 10 to the -2nd and 10 to the 2nd, sort of our medium Kc range. An example of a reaction with a medium Kc is Fe3+ iron ion reacting with the thiocyanate ion and making FeSCN, and this is also a complex ion, and the charge would end up being 2+. This is actually a really cool reaction because the iron is colorless, the thiocyanate ion is colorless, and this is orange. So it's kind of a cool reaction because you can see how it forms, and you can play around with the equilibrium and change how dark the orange becomes. So again, I want you to practice writing the equilibrium expression for this and check the posted answer key to see if you've done it right. The Kc value for this reaction is 200. So that's an example of a medium Kc value. Finally, we are on small Kc values. A small Kc would have a lot of reactant and a little product. What this means is that the reaction really didn't happen much at all, right? We start with reactants, we make product, but if we barely make any product, then the reaction barely happened. So we would be somewhere over here on our reaction range. So a small Kc value means the reaction favors the reactants, and a big Kc value tells you the reaction favors the products. The range here that we're going to be working with as small are Kc values that are less than 10 to the -2nd. An example of a reaction with a small Kc value is the reaction between nitrogen gas and oxygen gas to make nitrous oxide or NO gas. The Kc value for this reaction is 4.3 times 10 to the -25th. Really, 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 really tiny. And actually, for us, that's a really, really good thing that this is a very tiny Kc. Any ideas why? I guess I could just tell you to pause the video and think about it. So if you want more time to think about it, pause the video and think about it, but I'm going to tell you why, right? So do you know what the main component of air is? Right, it's nitrogen. Nitrogen is the main component of air. What component of air do we need the most? Oxygen. Right? So the air we're breathing in and out right now is full of nitrogen and oxygen. So if this reaction happened and happened a lot, it would turn into nitrous oxide, which is a poison. So instead of breathing oxygen, we would be breathing nitrous oxide. So it's a good thing that this reaction barely happens at all, so that air stays filled with mostly oxygen and not mostly oxygen, mostly nitrogen and oxygen instead of the NO gas. All right, practice this. See if you can write an equilibrium expression. Okay, another thing that you should be able to do with equilibrium is calculate the constant from the concentrations. So that's what this bottom practice problem is doing. We're given a reaction. In this case, it's between hydrogen and iodine to make HI. And we are given a set of equilibrium concentrations. And we're asked to find the equilibrium expression and then judge whether or not this is a big or small value. So, in order to do this, we first have to make an equilibrium expression. Kc will be equal to the products, which are HI, and there's two of them, so that gets squared, over H2 times I2. So that would be our equilibrium expression. Now we would plug equilibrium concentrations into this. So this would be 0.78 squared over 0.11 times 0.11. So you do the math, and you should get 50 for this. So that's how we work from concentrations to a Kc value. You have to make sure when you do this that you are working with equilibrium concentrations, not initial concentrations. All right, so was this a big value or a small? Right, this would fall under the medium category. So not big or small. So as I just said, in order to find the equilibrium constant Kc from the concentrations, they have to be equilibrium concentrations. But what if the concentrations you have aren't equilibrium concentrations? Then what? Then we can use something called reaction quotient, or QC. QC is pretty much the same thing as Kc, except we're not required to be at equilibrium. So the formula for QC is the same as the formula for Kc. So if we have a reaction, AA plus BB goes to CC and DD, the reaction quotient QC will be the same thing. It is CCD raised to the power of D over A B. The difference is that these concentrations can be any concentrations. They don't have to be equilibrium concentrations. So So they could be your initial concentrations. They could be concentrations that exist right after a reaction starts happening, but before it's reached equilibrium. Okay, so QC and KC mathematically are set up the same way. The difference is that these can be any concentrations, not necessarily equilibrium. Okay, what that means is we can compare QC and KC, and that's going to tell us what direction a reaction would be moving in. So if we have a QC value that is smaller than KC, that's going to mean that the reaction is moving forward. Reaction is moving forward. Or in other words, reactants are becoming products. If we have a situation where QC is equal to KC, that means that the reaction is at equilibrium. And what that means, as we learned on the first page of this handout, is that the reaction is going in both directions simultaneously. So it's moving both forward and backward. If QC is greater than KC, that means that the reaction is moving backwards. So product is reacting backwards to form reactant. So if we don't know if a reaction is, if it's not at equilibrium, then we can use this relationship. So let's do an example problem for what this would mean. So we have a reaction and we're given the Kc value. The Kc value for this reaction between A2 and B2 to make AB is 2. Which of the following diagrams represents an equilibrium mixture? So what I want you to do when you sort of do this problem is assume this box is 1 liter, right? And each dot is 1 mole. So what we would have here in box A is we would have 2 molar A2, right? So this would be A2. We'd have 1 of them, 2 of them. That would give us 2 moles in a 1 liter box. And we would have 1 molar B2, and we would have 2 molar AB, right? 2 of these and then 1 of those. And because it's in a 1 liter box, the molarity is just equal to the number of dots. Okay, so that's going to be how we get our concentrations. We're going to take those concentrations and plug them into the QC expression and then compare it to Kc. So for box A, the equilibrium expression for this particular reaction, let's write that down here, right? So for this particular reaction, the QC expression is the products AB squared over A2 times B2. Okay, so in this first one, QC is going to be equal to 2 squared over 2 times 1 molar. This is going to give us 4 over 2 or 2. QC is 2, Kc is 2. So that means box A is at equilibrium. Why don't you go ahead and try this for the rest of them and then pause this, try it. When you think you have it right, press play and see how you did. Okay, so you should have gotten that box B, QC is equal to 2, so it's at equilibrium. Box C, QC ends up equal to 2 again, so it's at equilibrium. And box D, QC is equal to 4, so it's not at equilibrium. QC is greater than KC, 4 is bigger than 2, so the reaction should be moving backwards. Okay, so this wraps up the first part of your equilibrium lecture. We're going to later, tomorrow and Friday, learn about Le Chatelier's principle, factors that affect or stress out a system that's at equilibrium. And we're also going to learn how to use something called Rice tables to solve equilibrium problems.